The electromagnetic radiation is composed of light at different frequencies and thus different energies. Only some types of radiation are visible to the human eye. We call it optical or visible light. X-rays are much more energetic, but those produced in the universe cannot reach the Earth's surface because they are absorbed by the oxygen and nitrogen in our atmosphere. Thanks to the X-rays, we can discover the hottest places in the universe, those where gravity is more intense or where the most energetic processes happen. X-rays give us information about the gas at millions of degrees in the galaxy clusters, matter falling to black holes, gas exchanged by the stars in a binary system, or gas heated by the star explosions that we call supernovae. To observe the X-rays of the universe, we cannot use telescopes with conventional lenses and mirrors, since X-rays are not reflected by them. Instead, they go through them. To reflect X-rays, we use mirrors made of ceramic or metal shells, coated with a very reflective material. Focusing X-rays to obtain an image requires the mirror surface to be almost parallel to the light path, so that it simply bounces off its surface when passing, like the stones that skip when thrown at a lake. But by placing the mirrors like this, a central hole is left which loses a lot of X-rays. The solution is to place several mirrors nested inside each other, like the layers of an onion. Nested mirrors are very heavy, and in space everything adds up. Silicon pore optics (SPO) is the new technology that will carry ESA's new mission, Athena. It uses very smooth silicon wafers, like those used for computer chips, which are cheaper and lighter. These wafers are shaped to form a very light but robust structure of millimeter-sized pores. Scientists continue doing research to develop the X-ray telescopes of the future. They study new optical designs, such as the lobster eye, new mirror technologies, and new coatings for mirrors, all with the aim of improving the telescope's collecting area, its angular resolution, or its field of view. The combination of Athena's mirrors with the Wide-Field Imager instrument will allow for much more precise and deep X-ray sky mapping than with previous missions, revealing unknown populations of forming supermassive black holes since the dawn of the universe, and the formation of the first components of the gigantic structures we observe in the universe today. The power of Athena's mirrors, coupled with the exquisite precision of the X-ray Integral Field Unit instrument, will reveal the physical conditions of most of the ordinary matter that exists today. We will also unravel the history of how the elements of which we are made have been formed, or how is the material near supermassive black holes and how they shape the galaxies that host them. Athena, unveiling and understanding the hot and energetic universe.